Hello, everyone. If you've ever wondered how social your school is compared to other schools, or what you should be doing at a networking convention, or how strong are the bonds that are made at political rallies, those are all sorts of questions that can be answered by something called network science. And it's a growing, increasingly popular field of study that are used by scientists and business analysts alike, and even physicists. So in this sort of playlist that I've lined up here on YouTube, we're going to be going through why network science is so popular and how you might be able to do some of the basic functions in network science. We're going to be taking you all the way from how to set up your network data to how to make very sweet network graphs to judging things like centrality and identifying groups and how you might be able to use network objects to answer sort of bigger, more empirical questions. So I'm really excited to share all of this with you all. In this video, we're going to be covering just some of the fundamentals of how you do all of this in R and how you sort of read in the data, the different kinds of network data. And from there, we'll move on to more complicated subjects. But in the description, you can follow the whole series, and you can also find timestamps to go throughout the video to answer questions that may be more directed towards the gaps in your knowledge. And if you have any better ways of how you can do some of this stuff, let me know in the comments. But enough of me blabbering on. Let's head on over into R, and I'll show you guys what's up. So here we are in RStudio, and you guys can find a full link to everything that you see here on my GitHub, which will be linked below for a repository of all this network stuff. But essentially what we're going to be doing in R today is just looking at how to set up different kinds of graph objects for network analysis, some of the basic statistics that you can do for network analysis, how to read some of the graphs, how to read through some of the objects, a little bit of math, and everything in between. So let's get into it. There's a lot to cover. So basically the two packages that we'll be using here is the iGraph data package and its associated iGraph full package. iGraph is the most popular package for network analysis in R. There are a bunch of other packages that are better or worse depending on the scenario, but for the most part we're just going to be using iGraph. And then we'll set the seed. So whenever you deal with computers, know that randomness isn't fully random, and in order to keep the graphs some of the same ways and to lock in the randomness a certain way, we'll set the seed to Jenny's number, which is 8675309. Great. And so the first type of network object that we'll be pulling in is called an edge list. And an edge list is, if you think of Excel, will just be the rows are the connections, and the different nodes are the two columns. So here, 1 is connected to 2, 1 is also connected to 3, 2 is connected to 4, and then notice that 3 is connected to 1. So both 1 is connected to 3 and 3 is connected to 1. So this is a directional network. I'll also pause for a moment and just say that my vocabulary is that edges are the connections between nodes. Sometimes nodes will be called vertices, and depending on the field of study and the particular project, that language will be swapped around frequently. So just know that sometimes when you look at different stuff online, it may have a different language, and you may already know what it is without knowing their particular notation or language. Because network sciences spans physics as well as the social sciences. So if we run this, we'll get our graph object. Oh, first we need to run this. So we loaded in our packages, and I'll just clear my environment. So we loaded in our packages, we got our seed set, and then now if I assign the graph object, we get the first graph in the global environment here. So let's go ahead and take a view of that. So these iGraph objects, if you were to just run them by themselves, you'll get a simple printout that this is a directed network, as I described, and that there's 5 nodes and 7 edges. And then these are all of those directed connections listed here. So great. Another way to view this is just by running the summary, and you'll get the top line of everything. So this is a directed network, same as before. If we plot this by just surrounding the graph object with plot, you can see the basic iGraph plot object gets pulled up for us here, and then we can read this to see how all the nodes are interconnected. And then also note that while here I entered in numbers that 1 is connected to 2, we can also add sort of another dimension and put in people's names here. And then also if we set this to be directed equals false, that means that this is no longer a directed network. So now G2, if we were to plot this, we will see that all of those arrows go away, and Fatima is connected to Chris, and they're connected to each other. Maybe they share a locker or share a classroom, or we're co-authors on a paper or something, but there isn't really directionality there. They both just mutually know each other. And so great, with that, let's run the summary, and we'll see here that instead of directed, it's now UN, which is undirected, with 7 nodes and 10 edges. And then also we have one attribute called name, which is our a vertex, a vertice attribute. So you see this V here. If we want an adjacency matrix, what an adjacency matrix is it's similar to an identity matrix, where basically our X labels and our Y labels, to put it simply, are the intersection of those two on the matrix level will detail what the connection is. So if we run G1 with empty brackets afterwards, we can get our graph 1 adjacency matrix. So you see that node 1 here is connected to node 2, so there's a 1 there. Another way to get this is use get.adjacency. And here we see Anand is not connected to Anand, so there's not a loop there. He's not interconnected, but depending on your research project, that may be something you're interested in. But Anand is connected to Beth and Chris, because there's ones there, but Anand is not connected to Dieter, Sun, Ali, or Fatima. So another two functions that you should be used to is this E and V. E is for edges, V is for vertices. And then this is how you just get the details of the edges. So 1 connected to 2, 1 connected to 3, or vertices, and you can get all of their names there. Another way to get their name is by, similar to a data frame, you would select the vertices of G2, that graph object, and then you get the iGraph object rather, and then you get the $ name using our language to pull up all their names here. So then it follows that you can plug in data in the same way. So let's just set the vertice of G2. We'll create a new variable called gender, and then we'll enter in all the data here. And if we pull this open, we can see all of the genders lining up to the names that we have specified in the graph object. Another way to do this is by set.vertex attribute on the graph object G2. So we're just building on top of that same graph object. And here we'll plug in everybody's age. Let's view that. And here we see everybody's ages down here in the console. And then also we can set different weights to the graph object by, instead of using the vertex, we can use the edge. So I'll just create sort of a replication of 1s and 2s, but different kinds of edge weights might be the amount of hours that people talk to one another, or the number of years that they've known somebody, or the number of houses that they are away from someone. Any sort of weight like that you want to sort of specify can be added in there. Here we just replicated 1s and 2s, and we have that count there. So now if we do a summary of G2, we can see that's still an undirected object with 7 nodes and 10 vertices. And we have here more attributes. We have the name, the gender, age, and this new count, which is an edge attribute. So now let's talk about karate data. So a long-standing classical training data set is this Karate Club data camp, where there are 2 factions that are rivaling each other. And one is surrounded by a Mr. High, and another one is a John, what is his name? John A. So John A. and Mr. High are running this karate club, and there seem to be 2 factions breaking out around them. And so we have this data set from our iGraph data package that we loaded at the start. We load this in, we see we get our karate data loaded in. And if you download this in GitHub, I've detailed exactly how you read this data and what it all entails, so you can play around with it a little bit more, but let's go ahead and plot it. And here we see our data a little bit more clearly, and it's actually colored out now. So we have our 2 factions, one is orange, one is blue, and they're surrounded by a John A and a Mr. High, which is an H here. And so if we want to do the vertice count, we could have done that by just looking at our iGraph object before. Let's go ahead and read this real fast. So this is an undirected weighted graph with 34 edges and 34 nodes and 78 edges. The graph is called Zachary's Karate Club, and it has a whole bunch of attributes. It even includes a citation to the original author's work here, as well as the author of the graph object, the particular faction that they're in, and even here there's a color for the different vertices here. So it's a list of blues and oranges, which makes graphing a little bit easier. So if we run a V count, we can get the same 34 as seen before, and E count for edge count, we get the same 78 as before. Also, we may be interested in the measure of degrees. And so the degree is essentially the on average connections. Well, that's how at least we're going to compute it here. If we run just degree karate, we'll find every degree for each actor, including Mr. I and John H, or John A here. So this is all of the connections that each one of them has. And if we run the average of that, now we have the average connections. So if we were to pluck out a random person amongst this group, odds are that it's going to be about 4.5 connections in the group. And so this is useful for comparing how many connections the average person has in a network, between networks, and then also networks over time. Another sort of descriptive statistic is density. And so density is it's pretty much calculated as like the amount of actual connections divided by the total number of potential connections that there could ever possibly be. And so you get this sweet percentage. And here we get 14% or 13.9%, basically 14, where the network is about 14% dense out of 100% density. And so this is sort of describing, how well interconnected the graph is compared to other networks, compared to the same network over time, compared to networks in similar social situations. And so if we wanted to measure, how chatty a nail salon is, we could run something like the density of chatter between people at this nail salon across all nail salons in the city to find the nail salon that has the most gossip spreading between it, for example. And I'm sure you could think of 100 examples better than that, but that's just one that comes to mind for me. So here we also see the diameter. And the diameter, similar to a circle, is just the measure from one node to the other one. And so here we see a diameter of 13. So the longest path that we have is, we can't really tell from the graph object, but probably 17, and it has to travel 13 times before it ever hits 27 there. And here we can use get diameter to see this long pathway, or a portion of it. And so it starts from actor 16 to John A to actor 20 to Mr. High. But actually, a better way to get this is by using farther vertices. And here we can see this pathway a little bit more clearly. So it goes from actor 16 to actor 17. And so that's sort of our longest vertice here in the network. And that's our age, or our distance of 13. So all three of these, both the degree, density, and diameter, we'll be going into more detail down the road. But these are sort of three primary descriptive statistics to define your network object initially right off the bat after you load in the data and kind of start exploring it. Another thing we can do is we can beef up this plot object a little bit and use some of these variables that we just discovered to inform our graph object a little bit more. So what we'll do here is with the edge width, we'll make the edges of our graph a little bit stronger or lighter depending on the weight of connection, which our karate data is a weighted graph, so we'll throw the weight into the graph object. And then also the vertex size, so the circles there, we'll make those bigger depending on the number of degrees that they have. So we'll use these circles as another sort of variable that we can use to analyze. And then I'll change some of the other labels and stuff. And so if I run this plot, now we can see probably the world's most disgusting network object, but here it is. So we see that the degree creates these circles being bigger. So Mr. High namely has student 2 and 3 on his side, and they're very well connected, but somebody like student 7 or 17 down here are barely connected at all. And in fact, they're farther away depending on their edge width as well. So they're pretty shot out to the sides here. So it's namely this inner core of people surrounding Mr. High. And then conversely with John A, you see that his degree centrality, or his degree, is very well connected here. But also you have the student 33, which is very connected as well. And so it's mostly John A with one student sort of leading all the other pack, but Mr. High is a more sparse sort of network community there. But these aren't the only kind of graph objects and network data scenarios that we have. So we've covered adjacency matrices as well as edge lists, but another way to view our data is through these bipartite networks. So this is where you have a relationship between nodes in that they're only connected to another party. So if I love Jim from The Office and so do you, we are a connection. Or the fact that we both watch The Office, we are a connection. I don't know who you are, you don't really know who I am, but we've both watched The Office, so we're a connection. So here, how we can set up this data is first we'll set up a matrix, which has all of our connections in it, and then we'll set the number of rows, and we'll create this mem, which is probably a terrible name for an R object, but let's go with it. And then we'll create the dimension names, group 1 and all these Y groups. So we're just labeling the names here, and then here we have something similar to an identity matrix, but this is really a bipartite graph. And so this is that Y1 is connected to group 1, Y2 is connected to group 1, so is Y3, but Y5 is not connected to group 1 because it doesn't have a 1 there. And then you can read the same for group 3, and as however many groups or schools or research papers that we've read or whatever we want to be connected by, we can run that down as far as we want across all the individuals in the columns there. And so let's make this into an iGraph object using graph.incidence. And now we have an iGraph object. We see it's undirected, but it's a bipartite network, which is what that B at the end there is. And we have 8 nodes and 8 edges, 8 connections between them. And here's all of those connections for us. So cool, let's go ahead and plot this and take a look at what it looks like. You might be able to learn things a little bit easier here. So Y2 and Y3, yeah, they're connected, but they're only really connected by knowing group 2 and group 1 together. And then Y1 is connected to 3 people, but only through group 1's connections. And so this is a graph that includes both the groups and the nodes within them. But if we create this projection, bipartite projection, this function will sort of rip apart this graph object and give us 2 things. We can now view through plotting the projection, which is PR, which was our graph object here from projection, project 1, and then I just made the edge width here be stronger or weaker because this is a weighted network. And so so now we only view the groups. So group 3 is kind of weakly related to group 1, but group 2 is pretty strongly related to group 1. And then here we can view just the nodes again if we want. So all of these nodes are not connected directly to each other, but they are connected directly to each other in the fact that they are connected to a group. So we just kind of cut out the middleman and connected the groups together here and created weights for how strong they are connected. We can also get an adjacency matrix here if we wanted by get.adjacency on these projections. Similar to before, we can create this adjacency matrix for ourselves where the diagonal is zeros, and we can see how well the groups are interconnected for our graphs if we wanted. Here's the same thing for the particular y variables within those groups. And you might wonder, well, what exactly is this function doing? We'll be using it a bit in future videos, but what the math behind this is we take our original variable, our original matrix object, mem, and then you use matrix multiplication, which is where in R you surround a multiplication sign with parentheses symbols by the transpose of that matrix, which is what T does. And so if we run just this, we'll see that this affiliation group does have loops on it. So group 1 is connected to group 1 4 times, which for certain projects may make sense, but for ours, let's say it doesn't. So on the diagonal, we can populate that with zeros, and then we will get the the same identity matrix or the same adjacency matrix as before that we used with the actual function. We just did it mathematically, so it's the same thing. And we could do things for the other side. So that's it for this video. I hope you guys learned something. If you did, feel free to leave a like. But after kind of learning these fundamentals of network science, we can really start connecting the right method with the right questions that we have about the world. And we're off to the races, kind of learning a lot. I'm sorry if this particular segment was a little bit dense. It's that way kind of on purpose because if you mess up some of the fundamental steps of building your network model or your data, then you can just royally mess up the entire project, and everything to follow is kind of biased and not really trustworthy. I'll leave a link to an article about this from Carter Butts in 2009. It's a science article, may be worth watching. You can see a little bit on screen now, but feel free to check that information out just to kind of get a solid foundation. Basically, don't mess up your data. Don't mess up the start of your project. Otherwise, it's all going to go wrong. But yeah, in the next video, we're going to be covering centrality, which is great. We're going right into some of the statistics of network analysis. Yeah, and I'll see you guys over there. Bye.